Hi, my name is Jianan Zhang and I'm a postdoc in Professor Li Deng's group at MIT. In this presentation, I'm going to share our work on using flame spray synthesis to produce a cathode material for lithium-ion battery. Our specific focus is on using additives for morphology control and the performance optimization. First of all, I want to talk about the background and the motivation of our work. We know that in recent years, there are newly developing areas in energy application, such as the transportation electrification, especially electrical vehicles, and grid energy storage for renewable energy, such as wind and solar. In these applications, the most important part is the energy storage method. Lithium-ion battery, which has a relatively high energy density, is a promising method for energy storage. And in fact, driven by these newly developing applications, the demand for lithium-ion battery is predicted to increase dramatically in the next 10 years. Although it's a promising method, there are still challenges faced by the battery. For example, the cost is still relatively high, and it also needs improvement on energy density, the charging rate, and lifetime. All of these are related to different parts of the battery. And one of the most important parts is the cathode material. Cathode material has long been known as the mean capacity limitation and a cost contributor to the battery. For example, the cathode material alone takes about 39% of the total material cost. One of the promising types of cathode material is multi-component metal oxides, such as lithium, nickel, cobalt, manganese oxide, that is also called NCM. The commonly used commercial method for producing NCM cathode material is the co-precipitation method. This one can be split to two steps. The first step is the precursor synthesis, and next is the lithiation. In the precursor synthesis step, all of the metal elements except the lithium are precipitated in batch reactor to form solid particles. The particles are then collected and for the next step, lithiation. In this step, the precursors are mixed with the lithium source and then annealed at a high temperature condition. The co-precipitation method has a lot of benefits, such as it has a good control on the morphology, and it also can ensure a good homogeneity of different metal elements. However, it also has some drawbacks. For example, it's a non-continuous process and has relatively complex synthesis step. And in each step, the processing time is relatively long. For example, in both steps, it takes about 10 to 20 hours to finish. This makes the manufacturing cost is relatively high. Right now, about 46% of the cost is from the manufacturing. Therefore, we are exploring new methods that have relatively light steps and relatively short time. One of the promising candidates is the flame spray synthesis. This method also has two steps, with the first step as a material synthesis. In this step, all of the metal elements, including lithium, are dissolved in the solution. The solution are sprayed in a high temperature chamber to form solid particles. The particles then collected and for the next step annealing to get a good crystal structure. This method has a couple benefits, such as it has a relatively simple processing step and is a continuous production method, and has relatively short synthesis time. We expect that it can reduce the processing time by at least 50%. For spray method, the smallest element, in fact, is a droplet. For the droplet, it is initially in the liquid phase, and then after the solvent evaporation, the metal ions precipitation, and the raw material decomposition, it forms a solid particle in the end. During this process, the solution and operating condition are two major factors to affect the final product. Depends on the solution and operating conditions, we can get a particle with a dense structure, or this shell structure, or a loose structure with the small particles agglomerated together. For the solution, the parameter to consider is about the type of solute and the solvent and the concentration. And for the operating condition, we need to consider the parameters such as the temperature, the residence time. In our current work, we focus on the solution first. The parameters such as the types of solvent and the solute and the concentration have been studied a lot before, and we want to explore new parameters that can affect the final product. We found that Introducing additives has also been an efficient way to change the morphology and the performance of the material, but it has relatively less studied for cathode material production. There are different types of additives. We roughly split it to two categories. The first is non-polymer material. For this one, we use urea as the representative since it's relatively abundant material and have low cost. Another category is the polymer additives, and we use the PVP as the representative of the polymer additive in our current work. This slide shows the experimental detail of our work. In our current work, we are synthesizing NCM811, which has a chemical formula listed here. It has a transition metal, nickel to cobalt to manganese, with a ratio of 8 to 1 to 1. The first step is solution preparation. We dissolve different types of metal salts in deionized water together with the additive. For PVP, we add 1 and 2 weight%. For urea, we tried 2.5 and 5 weight%. Then solution was fed to ultrasonic sprayer that is used for generating droplets. The droplets are carried by air to two preheating sections before they go to the high temperature burner. The burner used a premixed methane flame as a heat source. After it's passing the high temperature burner, solid particles form and they are collected by the filter. After they collected, they were post annealed at 450 for 4 hours and then 750 degrees for 13 hours and oxygen atmospheric condition. At this step, we consider the material is synthesized and then it was characterized by different methods such as SEM, X-ray diffraction, and the electrical chemical test. This slide shows the morphology of the sample we got. We focus on two main factors. One is the size of the particle. For all of the samples, we can get the particle with a size around 1 micron. And the second feature I want to show is the porosity of the particle with different additives. First, let's take a look at PVP. When we add PVP, we found that at 1% PVP addition, the particle shows more porosity when compared to the one without any additives. When we increase the concentration of PVP to 2 weight%, we can see the particle become more porous. In contrast, when we take a look at the urea addition, it seems like a relatively less effect on the morphology when compared to the one without any additive. We can see the particles generally still solid. We take one more step to add urea in the solution with the PVP. We compare the result and we can find that as long as urea is added, it can inhibit the porous structure of the particle. The hypothesis is that for PVP, it's not only a polymer, it's also a bender material. When the droplet is evaporating, the metal ions start to accumulate on the surface of the droplet. Without additive, this metal ion still can diffuse inside the droplet. However, with the PVP, it hinders this diffusion process and causes the surface enriched with the metal ions more and more, and eventually it forms this shell structure. As a comparison, for the solution with urea, during the heating process, urea starts to decompose and release gas. This gas can disturb the formation of the shell and eventually get a more solid particle. This is the X-ray diffraction result of the sample we synthesized. We only use this one to confirm the sample we got had a good crystal structure. For NCM811, it has a layered structure listed here with the transition metal as one layer and lithium-ion in between. We only focus on two features. With the first one is whether this structure is organized, a layered structure or not, and the next is whether we have a low level cation mixing. For this layered structure, we can tell whether it's organized or not by two pairs of peaks. With the first pair is 006, 012, and then the other peak is 018 and 110. As long as we can see split peaks, we can tell this structure is organized. The next feature is the cation mixing. For this layered structure, lithium-ion sometimes mix with the transition metal, which is undesired for the material synthesis. However, as long as the ratio of 003 over 104 are higher than 1.2, we consider the material has relatively low level cation mixing. All of the samples have a ratio higher than 1.2, so we confirm that they have a relatively low level of cation mixing. At this stage, we confirm that the samples we have organized layered structure and low level of cation mixing. Next, let's take a look at the electrochemical performance test. First of all is the battery testing. We test our sample with the CR2032 coin cell with the current density at 1C defined as 200 mA per gram. This figure shows the first cycle charge discharge curves of all samples at 0.1C. We mainly focus on two features. The first one is the discharge capacity, and the second one is the Coulombic efficiency. Results are summarized here. For the one without any additives, it has initial discharge capacity around 196 mA per gram and a Coulombic efficiency of 88%. When we add 1% PVP, the discharge capacity increased to 199 and the Coulombic efficiency also increased to 91%. However, when we add more PVP, both the capacity and the Coulombic efficiency decrease. In comparison, when we add urea, we can notice that the discharge capacity both decreased and also with decreased Coulombic efficiency. For typical NCM 8811, the first cycle discharge capacity is in the range of 195 to 205 mA per gram, and the Coulombic efficiency in between 87 and 91 at 0.1C. Besides the first cycle test, we also take a look at two more features. The first one is the capacity at a higher current range, and the other is the cycling performance. For the discharge capacity at a higher rate of 5C, we can notice a similar trend to the one at 0.1C. That is, when we add 1% PVP, the discharge capacity increased. However, when we add more, the capacity decreased, and we notice relatively low discharge capacity for the one with the urea addition. Then let's take a look at the cycling performance. We test the capacity after 35 cycles at 1C and see the retention ratio. We can notice that for a relatively low level of additives, the retention ratio has a minor change. However, when we add additives more, either for PVP or urea, the retention ratio will drop. Overall, the samples with PVP addition has relatively better electrochemical performance than that with the urea addition. Then we try to understand what's the reason for a better performance that's achieved by PVP addition. So we conducted the electrochemical impedance spectroscopy test. This method was done by providing low level of voltage perturbation to the coin cell and then measure the current output. Then we related this current output with the voltage input, and we can study the features related with the coin cell, such as the resistance. In our current test, we input the voltage with a frequency from 1 MHz to 1 mHz. And this is the next plot of the result. In this plot, the first point stands for 1 MHz and the last point stands for the 1 mHz. And this is the overall data set. In next slides, I will show the details of the local features. So the local feature in figure A was enlarged and shown in figure B. When we take a look at the two curves, we can notice there are three semicircles on both curves, either for the one with the PVP addition or the one with the urea addition. These three circles in fact stand for three different types of resistance, with the one at a relatively high frequency stands for the surface film resistance that is result of the solid electrolyte interface formation during the charge and discharge cycles. The second one, the relatively medium frequency range, is the electronic property of the material, or you can consider it as the resistance of the material itself. Last one, the CLF, at a relatively low frequency range, is the charge transfer resistance. It is the resistance that characterizes the transfer of the electron between the material and the electrolyte. We can roughly tell the magnitude of the resistance just by the size of these semicircles. When we take a look at the first two types of resistance, we can notice that for the one with the PVP addition or urea addition, they have a relatively similar amplitude. However, for the charge transfer resistance, we can notice a dramatic difference between these two samples. For the one with PVP addition, it has a significantly lower resistance than the one with urea addition. And we believe this is the main reason why the one with the PVP have a better electrochemical performance. And we want related this electrochemical performance with the morphology of the particle. For the one with the PVP addition, we know that it increases the porosity of the particle. The increase of the porosity will create a more surface area, so it ensures a better contact between the material and the electrolyte. However, urea addition results in more solid particle. Then the surface area is relatively less than the sample with the PVP addition, and this results in a higher resistance. That is the hypothesis why the one with urea has higher resistance than the one with the PVP addition. As a conclusion, we confirm that using additives is an efficient way to control the morphology and the electrochemical performance. Overall, compared with the one without any additives, PVP can improve the electrochemical performance but result in a more porous structure. In contrast, urea can get a more solid particle but will worsen the electrochemical performance. I also want to emphasize that the current work only focuses on the solution part, but as I mentioned before, the operating condition is also an important parameter to consider. Therefore, we believe we can optimize the performance further by changing the operating condition and the post-annealing parameters. In the end, I want to thank Professor Zhu Li and Yimeng Huang from the Department of Nuclear Science and Engineering at MIT for their support in battery fabrication and testing. I also want to thank you for your attention and your interest in our work.